Okay, so we're going to continue our talk on topic 4.4, and we're going to start talking about interference. I'm going to see how well I can do this and keep this within a decent time frame. So imagine you have diffraction. So you got diffraction, you got a wave that, remember that concept of diffraction, the key of that was that whenever a wave whose wavelength is comparable to or bigger than the size of the aperture, or an obstacle attempts to move around, it can move around it, you can get diffraction. So let's continue on with this. So what happens, I'm going to go quickly through some concepts of diffraction. So what happens if you have, for instance, a slit like this, and you have waves, here's the wave fronts approaching it. So when they encounter this slit, and I try to make the slits about the same size as the wave lengths. I know it's a rough drawing, but it'll work. You can get the idea. And so imagine, that therefore significant diffraction will take place, and you'll get this. It won't be as bright over in this area, you guys, but still, you get the idea, right? And so according to Huygens' principle, you get something like this. It doesn't look good there, but that's okay. All right. So, and I'm going to change color and make that yellow. And so the same would occur over on this one. So they're branching out. Not a good drawing, but you can see though. Let's just take right here. Let's just look right. Let me pick a different color. Let's pick that burnt orange or something, whatever you want to call it. Let's look at that right there. Notice right there that they overlapped. So if you think about that, they could overlap at many places along where the waves are interfering with each other, occupying the same space at the same time. Especially, now remember that the key about this is that these are all emanating from these waves back here. And so they're typically, you would see this in like a monochromatic, coherent light source. By that I mean one color, and they're all in phase. So if you had a screen, like I do here, then if you looked along this screen, then at certain places along the screen, the waves would overlap and they would be in phase, and then in other cases, they would be about 1/2, difference in their phases, so you'd have constructive where they're in phase and destructive where they're out of phase. And if you take a look, and let's just make this with a nice purple. And so if you think from this slit here to some point over here, and now remember this is very small angles, so we can consider these to be sort of parallel. Then if you look along here, then what we end up having is a nice little triangle. And you can see that if this little distance right there, that little distance right there, and remember this is very, very small. My diagram is huge compared to what's actually taking place. But you did get to see a little bit of this take place today in class, and we'll get to see it more in the lab. If that distance were equal to, such that the distance from here to here is the whole number multiple of the wavelengths plus 1/2, and this distance was just a whole number multiple of the wavelength, then they would arrive out of phase and you get destructive interference. If this distance, if you move down here a little bit more, and this distance from here to here now it ends up being a whole number multiple of the past. Maybe that takes 30 wavelengths to get there. I'm just making up a number, and this one takes 20 wavelengths to get there. But think about that. They're both going to arrive at the same time, and they will be in phase. So you can actually put some math here, a quick equation, which you're not really responsible for, but would be this distance, we'll call this distance d, and we'll call that angle theta. And so we'll take d times the sine of theta equals n times lambda. And that n is some whole number multiple of the wavelengths. And from this you can see that d you could figure out, and you could solve for this. If that ends up being, you can solve for this side here. And well, anyway, let's go forward. All right, so in your book, they talk about, what you're responsible for in terms of interference is something that takes place along a straight line. So here we have a source of sound, for instance, or light, and here we have a source. And let's just pick some point between it, and we'll call that point, just where you're standing, for instance, if it happened to be sound. Excuse me. So if you think about that, then if you were right here, then waves would be coming from here and here. And if let's make sure that let's assume that they're the same source, same wave, same frequency, and the medium is consistent throughout. So the distance. So if we go that velocity is equal to distance over time, then the time it takes for that wave to get there would be distance over velocity, and the same would be true for this side over here. So both of these you could define their time to get there by a distance over velocity. Now remember, they're the same wave, so they have the same velocity. So since I built up that model for you in this previous slide right here, that you could get interference along this plane here, then couldn't you see that you could also get, what if this wave from here arrived at just the right time? Now remember, we're talking about points along here, but just the right time, such that it was a half out of phase. This side was a half out of phase with this wave at that particular point right there. Then what you have is destructive interference. And then if you moved along maybe a little bit further down here, you all of a sudden find out that, now I see I've got constructive interference, because now the distance from here to here is a whole number multiple of the wavelengths, and the same can be said here. And so you end up having constructive interference. So we're going to look at constructive and destructive interference from that point of view. A little bit different. So if we do that, then we can say that and remember, they both have the same period, so we could say that d, we'll call this d1 over v minus d2 over v is equal to n, some whole number multiple, or integral, is I think your book might call it integral multiple, but I don't know. You call it what you want. And times the period of the wave. So if you look at that, if we were to just solve this for d1 and d2, so d1 minus d2 equals, and we move the v over since they're a common denominator, we can factor that out, then it would be nt times v. But recall that what is the wavelength of any wave? Well, the wavelength is you could find that as velocity equals frequency times lambda, but don't forget that frequency is just 1 over the period, so we could rewrite it as velocity equals 1 over the period times lambda. And if you move t over, then lambda equals velocity times the period. And is that right? Yeah, I think so. Velocity times the period. So we could replace, we could solve for, let's see, we could get rid of TV, because T times V is lambda. Isn't that right? Because we just said that taking this down right here, this way, we can say that lambda equals V times T. Oops, sorry, wrong T, but that's capital T. All right, so we're going to rewrite this as D1 minus D2 equals N, and we're going to replace V times T, which this really looks horrible over here, but that's V times T, that's lambda equals V times T, lambda. So taking that over to the next stage, D1 minus D2 equals N lambda. And if you meet these conditions, where D1 minus D2 equals some whole number, some number such that it's equal to the where you get the constructive interference and times its wavelength, then you have constructive interference. However, if you meet these conditions, let me rewrite that. if you meet these conditions, d1 minus d2 equals n plus 1/2. Well, think about what that's going to do. So now you've got this whole number multiple plus 1/2 of a wavelength, and you're going to get destructive interference. This is destructive. And so it's really basically all up to the path difference. So I need to stop right there because I got to 10 minutes. And guys, I know I tried to say 7 minutes or so in class, but to get a concept across, it takes a little time, even as fast as I talk. But we will look at this in class and we'll close it up, and you'll be ready to understand constructive and destructive interference, and make sure you review that concept of diffraction too, because that sort of helped you understand how you can get some of this. Okay? All right, that's it for tonight.